Hello. Today we shall study trigonometric integrals. This is section 7.2. I want to focus on some most typical cases which most often appear in practice. And otherwise, this topic is very wide. We cannot exhaust all possible trigonometric integrals. So please focus on those that I will discuss here. Now, there are two trigonometric integrals which I mentioned already. If you have to integrate cosine kx dx, k is some coefficient, you get the derivative sine kx over k plus c, and this is good to memorize, not make substitution each time. And similar for integral sine kx dx. How to integrate a tangent? When we want to integrate the tangent or the cotangent, we switch to sine and cosine. So tangent is sine over cosine. I'm writing sine x over cosine x dx. And in general, when we do trigonometric integrals, we focus on two equations. The equations are sine x dx. This is negative d cosine x, because the derivative of cosine is negative sine, and the negative is for compensation. So this is an equation for differential. This comes from d cosine x over dx is negative sine x. That's the same equation. Also, we have another important equation. If you have cosine x dx, we write this like d sine x using differentials. So I shall put these two in green. So this equation and also this equation. Now we are going to use such equations to evaluate integral of tangent. Look here on the top, you have the product sine x dx, so I'm writing immediately negative d cosine x over cosine x. We can put the negative outside, and now this is d cosine x over cosine x. We can think of cosine x like new variable. No need to write use substitution. This is the something over the same thing. This is a logarithm. So we have negative natural log. We have to put absolute value cosine x plus c. And that's how we deal with the tangent, integral of tangent. If we have integral of cotangent, we do the same. We write in terms of cosine and sine. So this will be cosine x over sine x dx. On the top you have the product cosine x dx, which is d sine x over sine x. So think of sine x like new variable, and we integrate immediately. This is natural log absolute value sine x plus c. Okay, what we have a coefficient, let's say we have integral tangent kx dx. Just like above, this will be negative 1 over k natural log cosine kx plus c. So this is more general, and we just use the integration for sine and cosine the same way. Okay. Now let's look at some other very popular integrals. A popular integral is integral of sine squared x dx. How to integrate this? Now, before showing you the correct integration, I want to tell you that this is not sine cubed x over 3. It is not cosine squared x. And you see, I have seen such things in certain papers, so please don't show me such wrong works. These answers are wrong. It's very easy to check it by differentiation. You don't get the correct antiderivatives. Okay, so how to do it correctly? The integration here is very specific. It's based on trigonometric identities. We write sine squared x like 1/2 1 minus cosine 2x. It's a special trigonometric identity which is used for such cases. And there is a similar one for the cosine squared. Cosine squared x will be 1/2 1 plus cosine 2x. You can call them double angle formulas or half angle formulas because they come from the representation of cosine 2x in terms of sine or cosine. Anyway, these are two important trigonometric identities. I will put them in a green box like that, and that's what we're going to use when we integrate sine squared or cosine squared. Here, if we want to solve integral sine squared x dx, we use this representation 1/2 1 minus cosine 2x dx. So we take 1/2 outside and distribute the integration. So this will be integral just 1 dx minus integral cosine 2x dx. Integrating the constant 1, you get x. It's 1/2 x minus, remember how to integrate the cosine? We do sine 2x over 2. And at the very end, plus c. We can distribute 1/2. This will be x over 2 minus sine 2x over 4 plus c. That's the integration of sine squared x. Absolutely the same way we integrate cosine squared. Because the formula is very similar, I can write the answer immediately. You see, in the first formula we have minus, in the second plus, so the difference will be just in one sign. We have x over 2 plus sine 2x over 2 plus c. And that's it. That's how we do sine squared and cosine squared. What about integral cosine cubed x dx? How to solve this integral? Here we have again a specific approach. We factor cosine 3x. We write cosine squared x times cosine x dx. And cosine x dx we represent like the sine x. And sine x will be our new variable. What about cosine squared? Well, cosine squared is 1 minus sine squared. So I'm writing integral 1 minus sine squared x d sine x. At this point, if you insist, you can put u equals sine x or new variable, or you can just stay with sine. If I distribute the integration, this will be integral d sine x minus integral sine squared x d sine x. So integration is according to sine x. The first integral is just sine x. And for the second integral, we use power rule according to the variable sine x. So this will be negative sine cubed x over 3 plus c. And that's how we deal with the cosine cube. If we do the substitution here, if we use u, then we have to return to x. Okay, what next? Well, now I want to do some examples from the book. Here is number 2 from section 7.2. Evaluate integral sine cubed theta cosine 4th power theta d theta. Theta is our variable now. This letter is often used for angles, and here we have integral with theta. How to solve this? I notice here this sine cube, and I can approach it like I did with cosine cube with previous example. So I shall factor this way. Sine squared x, sine x separately, cosine 4th power x dx. Now sine x I shall move to the very end, so write it this way. It will be sine x dx, and sine squared I shall write like 1 minus cosine squared. And here we have this, there is a cosine 4th power here. And sine x dx becomes the cosine x with the negative, the very front. And see how this is written. Now you can think of cosine x like a new variable. Why don't we just use this time another letter for convenience instead of rewriting every time? We then don't have to do the u dx because it's already here. It's the u here. Written in terms of u, this will be negative 1 minus u squared u 4th power du. So inside the integral we distribute u 4th power. Oh, this will be negative u 4th power minus u 6th power, and this is du. And we integrate by the power rule. This will be negative u 5th power over 5, and now plus u 7th power over 7, and plus c. Returning to cosine x, so this will be, let's put the positive first, it will be cosine 7th power x over 7 minus cosine 5th power x over 5 plus c, and that's it. Okay. Oh, I'm sorry. I'm very sorry because as you see, the integral was written in terms of theta, and I continue with this x. I'm so used to this x. So we can think that x is theta. Okay, I'll be more careful next time. Here is number 6. Integral now t cosine 5th power t squared dt. Let's make better t squared here. How to solve this integral? The presence of this t squared and 1t in front, this shows you immediately that you have to go with substitution. So we make this substitution. Let's set x to be t squared. So the x will be 2t dt. The product t dt is present in the integral. T dt will be 1/2 the x. So we substitute dt by this. The integral becomes 1/2 outside cosine 5th power x dx. So how to deal with this? Okay, we shall do the same approach that we used for cosine cubed. So I shall write this factored cosine 4th power x cosine x dx, and then cosine x dx, this will be d sine x. What about cosine 4th power? This will be written cosine squared x squared, and here d sine x. Now cosine squared we replace by 1 minus sine squared, which, and maybe again it's good to use a new letter now. Let's say u is sine x. We replace sine x by this, and continuing this work, we have 1/2 1 minus u squared, all this squared, du. We can solve this integral by expanding this square. We have to compute the square. Just a polynomial. Here we have 1/2 1 squared, then minus 2 times the product, minus 2u squared, and plus u 4th power du. Simple polynomial to integrate. So we go term by term. This will be 1/2. Integral 1 is u minus 2u cubed over 3 plus u 5th power over 5 and plus c. Now I shall multiply in the parentheses by 1/2 and at the same time return to x. So this will be 1/2 sine x minus, here the second term becomes 1/3, reducing by 2, sine cubed x, then plus 2/5 sine 5th power x and plus c. And that's our answer. Oh, yeah. I almost forgot. We had to return to t. The original integral was back to t. Remember, x is t squared. So we have 1/2 sine t squared minus 1/3 sine cubed t squared plus 2/5 sine 5th power t squared plus c. I almost forgot about t. The next one. Look at this integral. 0 pi over 2 square root sine theta, and outside we have cosine cubed theta d theta. Now I shall be careful not to forget this theta. We have integral with limits and square root here. What to do? Well, we work with cosine cube the way we did before. So we factor it. 0 pi over 2, repeating this, root sine theta. So now we write cosine square theta, cosine theta d theta. Cosine theta d theta, this is d sine theta. Cosine squared theta, we shall write 1 minus sine squared theta. So again, it will be convenient to write u equals sine theta and work with one letter instead of entire function. So we do this substitution. du is already here. We have to change the limits though. When we have integral with limits, that's important. So when theta is 0, sine of 0 is 0. When theta is pi over 2, sine is 1, so limit here on the top is 1. We have root of u, then 1 minus u squared du. We're coming to this integral, no more trigonometric functions. How to solve this? We distribute root of u. And at the same time, I shall switch to fractional powers. Instead of root of u, I shall write u1/2. So when you multiply, you get u1/2 minus u1/2 plus 2. That's 5/2 du. Well, we integrate by the power rule. This will be u 3/2, adding 1. Have to divide by 3/2, which is multiplication by 2/3. And then the next term will be u adding 1 will be 7/2 multiplied by 2/7 and evaluating between 0 and 1. Evaluating at 1 is easy, evaluating at 0 is easy, so this will be 2/3 minus 2/7. Now we have to remember, work with fractions. Common denominator is 21. So the first fraction multiplied by 7, the second by 3. So this will be 14 minus 6 over 21. So that's, I guess, 8 over 21. Yeah, and we stop here. We have a numerical value, 8 over 21. Let's do another one. Integral sine cubed, let's write t this time, over cosine 6 power t dt. That's the denominator. And it's a little bit unpleasant, but it will be easy with the same principle. Sine cube with factor, writing sine squared t sine t dt. Below we have cosine 6t. Now sine t dt, this is negative d cosine t. Sine squared is 1 minus cosine. So it's good to write immediately u is cosine t and work with the substitution. So we have integral 1 minus u squared on top du, and one negative sign coming from the cosine, and below denominator is u 6 power. I will distribute the negative inside. I don't like this negative sign, very positive person. So this will be u squared minus 1 over u 6 power du. And then how to solve? We divide. Divide using properties exponentials. 2 minus 6 is negative 4 minus u negative 6 power du. That's the only way to integrate. And then power rule equals u negative third over negative 3 minus u negative 5 over negative 5 plus c. Simplifying, negative 1 over 3 u cubed plus 1 over 5 u fifth power plus c. Now, as I told you, I'm a very positive person. I should put the positive term in first and return to t. U is cosine t. So this equals 1 over 5 cosine 5th power t minus 1 over 3 cosine cube t and plus c. And that's it. Maybe it is good to finish with one simple and special integral. How to integrate tangent squared. At the beginning I showed you how to integrate a tangent. Tangent squared is not more difficult than that. But again, we have to remember, we have to go, excuse me, we have to return to sin, to write in terms of sine and cosine. So this will be sine squared x over cosine squared x dx. And then what? And then a simple trick. I'm adding and subtracting cosine to the numerator. Sine squared plus cosine squared is 1. So this will be 1 minus cosine squared x over cosine squared x dx. And then we simply divide 1 over cosine squared x minus 1 dx. In the first position we have secant squared, which is the derivative of the tangent, so integration is obvious. This will be tangent x and then minus x plus c. I showed you this evaluation without using one identity. The identity helps immediately. If you remember tangent squared x, this is secant squared x minus 1. That's exactly what I did here. But this identity is not so popular like sine squared plus cosine squared. In case you don't know the identity, that's what you do. You just complete to 1 on the top, and you practically come to this identity. Okay, we had enough with the trigonometric integrals. Next time we shall study trigonometric substitution. Goodbye.